Hello everyone. In this video, I'll be going through this paper titled "Provably Good Batch RL Without Great Exploration." So the authors are Yao Liu, Adit Swaminathan, Alek Agarwal, and Emma Branskal. So let's get into the abstract. So I've been doing a lot of videos on offline RL or batch RL. So this problem fits into the same regime as well. So batch RL is important to apply RL algorithms to many high stakes tasks. So since you don't have to worry about the safety, since you are already working with large data set which is provided. So here they present a few challenges which you have already seen in few of the papers before. The first one is the usual distribution shift, which says that a new decision policy may visit many states and actions outside the support of the batch data which is provided. And the second issue with the batch RL problem is overestimation, that your algorithm which uses some neural network kind of stuff for approximating the Q values or something like that, which might overestimate in the unseen state. So that is the second issue. So yeah, so they say that recent algorithms have shown promise but can be overly optimistic in their expected outcomes. Yeah, that talking about BCQ and Bayer papers, which they compare the current algorithm in this paper with. So yeah, theoretical work has been provided. Okay, so the strong constructibility assumption is something like shown here. So the ratio of your policy to the policy of the dataset policy. So this is the dataset policy, so which is usually bounded by a constancy. Yeah, this seems restrictive for all state transaction spaces. Like you would need a large C if a few state transaction pairs are very rarely seen. So yeah, so in this paper they make quite a mild assumption. So yeah, so here they show that a small modification to the Bellman optimality and evaluation backup. Yeah, that is they use some of the intuitive ideas from papers from BCQ, but there is a strong theoretical contribution in this paper. So yeah, right, we highlight the necessity of our conservative update and limitations of previous algorithms and analysis by illustrated MDP examples. So yeah, they provide some two MDPs which shows limitations of BCQ, Bayer, and such algorithms. Let's move into the introduction section. So here they first say that our algorithms use growing data, batch data as an replay buffer in the usual of policy algorithms. So yeah, the work on offline RL can help unlock potential large data set, may improve online RL algorithms. Yeah, so yeah, this and moreover, to add a point to this, as we have seen in the previous videos, that everyone has this observation made in the offline setting, that since you don't need exploration in this problem, so you have separated out the exploration part and the optimization of the RL algorithm. So yeah, so that is one of the other advantages you have, which you can probably use to unlock up some potential in the RL algorithms. So yeah, let's get back to the this introduction. So let's see, approximate PIs, approximate policy iteration, and approximate value iteration is being used, which are model free algorithms. So yeah, so these can be thought of as something like a least squares problem, so which I'll talk about later in this video. Let's see. However, deadly triad of policy learning, functional approximation, and bootstrapping poses a challenge for model free batch RL. So yeah, interested readers can look at this reference. For what kind of theoretical limitations you would find with these three challenges in the problem. So yeah, they mention one particular issue is that max in the Bellman operator may pick SA pairs in the areas with the limited but rewarding samples. Yeah, which can lead to overly optimistic value function estimates and other performance policies. So this is the overestimation problem. Yeah, let's go ahead. Different heuristic approaches has been proposed. They're essentially talking about bare BCQ here. Yeah. Our theoretical analysis of these methods are limited to tabular problem and settings, and practical algorithms also differ substantially from their theoretical prototypes. Okay, so now the literature focuses on safe batch policy improvement. Yeah, only deploying new policies if with high confidence they improve over prior policies. However, such works either assumes the policy class can be enumerated. Okay. Yeah. These are some constraints which you can put in your Bellman updates. These are the heuristic algorithms, and then now, yeah, over the last 2 decades, AVI and APIs are all being developed. Yeah, there has been a rich amount of work on these least squares problems, so yeah, it could leverage those theory. Now they again mentioned that about the concentrability assumption which the previous works use, which they avoid. Yeah, as I said, the ratio of the non-stationary policy and the batch data policy is bounded by a constant. Yeah. This was the issue which makes the constant C large if the dataset policy for certain action and state PSR is close to 0. So yeah. Let's go further. Some methods here. Obtain guaranteed scaling in the largest density ratio. Okay, which is yeah, so this is the assumption which the current paper uses as well. So yeah, we'll be looking at this closely in this video. So now where erroneous be identified through subsequent online data collection. So yeah, so that is it fine to just reach the suboptimal performance in this offline RL setting is a question to be addressed. Yeah. So the contributions in this paper seems to be, let's see, we'll output a good policy with respect to the batch data available. Okay, constructability is not assumed, but we algorithmically choose to focus on policies that satisfy a bounded density ratio assumption akin to. So our methods are guaranteed to converge to approximately best decision policy. So it's like converge to the best policy in the space of policies satisfying bounded density assumption. So the second point is saying error bound is the policy space dependent. So yeah. So further, if sufficient coverage of states, then our algorithms output near optimal policies. So yeah, if you have seen the video on the algorithm called moral, so even there they give guarantees like this, where if you have a data set collected which is rich enough, then you would get a policy closer to your optimal policy. So yeah, many recent state-of-the-art batch algorithms do not provide such guarantees. Okay, they're talking about BCQ bear to remind. Yeah. Our methods come from a minor modification of adding conservatism. So yeah, this is adding a constraint kind of a term in your Bellman operators. So yeah, let's go ahead. Our API algorithm ensures the desired doing the best is best with what we have got guarantee with the data set. And ABI, there is a weaker result. Then yeah, some practical implementations are done on discrete and continuous tasks. So yeah, we'll be looking in the further sections. Let's go ahead with the problem setting. So this is the usual setting in all the most of the RL papers. So there's an MDPM, which is a tuple of state space, action space, transition probability P, the reward function R, and the discount factor gamma, and rho is the initial distribution, I guess. Yeah, distribution over initial states. So yeah, consider the usual discounted reward setting and the Q value corresponding to that for every action. We'll come back to this figure 1 in a minute. Let's go ahead with the text right now. This lowercase v pi to be the expectation, so it is this one. So yeah, it is taken over the expectation of all the possible initial distributions. So yeah, this is the parameter which all the guarantees is given with. Yeah, just remember this parameter. Yeah, going ahead, like given data set D with n samples run ID from behavior distribution mu. So mu is the behavior distribution pi b which I've written earlier. So yeah, yeah, marginal distribution over states. Okay, this is to just take care, yeah, of the notations. It's okay. Now approximate value and policy iteration. Yeah, algorithms fit Q function. F is the fit function coming from. Is this a linear function approximation? Oh, yeah, I think it is, because they will eventually use the least squares method. So yeah, let's go ahead. Yeah, these two are the Bellman operators, T and T pi, the usual policy evaluation and policy iteration Bellman operators. So yeah, considering the probability simplex over pi, you can actually show T is equal to the max over T pi or the policy space. So I mean, this is the usual result in RL, so, or MDP per se. Yeah, you also define the hat versions of these Bellman operators, which replaces expectations with the average sample averages. So yeah, so in short, AVI iterates over this T hat to get the approximate solution, and API performs first the policy evaluation using T pi hat, and then you get the greedy policy according to the T. Yeah. So yeah, one of the important properties which you would need is that T hat and T hat pi are contraction operators in some space, in some norm. It depends on what kind of analysis you are doing. Either it is usually subnorm or the distribution norm on mu. It depends. If you are using Bertseker's kind of proof, then you would get these things. If you are using Monos's line of work, then you would get you would work with this. Yeah, so let's go ahead with the challenges for existing algorithms. So here, this is the section where they compare the on a specific MDPs with respect to other model algorithms. So let's see. So yeah, so here this is what I have been saying in this video. The non-stationary policy and the divided by the dataset policy is being upper bounded by a constant c. So this assumption is really strong, so yeah, they don't make this assumption here. And yeah, this might be the reason for whatever suboptimal results which the other algorithms might see. Yeah, let's go ahead. Yeah, they provide a small two bandit problem here. Let's go over this. We have two arms with means, let's say 0.9 and 0.1 under the dataset policy. So since the dataset is being generated by mu, we can get good policies. Yeah, the caveat is that need conditions on C for theoretical results, discarding bad policies. Yeah. So yeah, let's go ahead with the texture and then come back to these figures. Nevertheless, the standard consentability assumption has been employed in many prior works. API. API. Yeah, you could see like um, error bounds on policy iteration by Munoz et al. Yeah, and other references which are provided here for these kinds of analysis tools. Yeah, in practice, yeah, just to add a point here, I mean, you would need to go through these references just to develop your own skills, and especially the current papers kind of tools. You will get an insight only if you have gone through all the earlier works. Otherwise, you would be just reinventing the wheel. Yeah. Let's get back to the text here. In practice, these algorithms often diverge, yes, because it's hard to satisfy the assumption. Such empirical observations have helped motivate recent ABI and API works that improve stability and performance. Okay, now let's go ahead with this BCQL. Yeah, what BCQL does is only bootstraps value estimates from actions. So basically what it does is you would have a target queue object which is constrained on the potential actions decided by some generative model which is trained on the dataset. So yeah, there's a really TLDR version of what BCQL is doing. So next they provide a short description with bear, which is the version which is like the BCQL version but with using non-zero threshold. So this constraint is not soft. Yeah, it's not hard, I guess. It's soft threshold. So yeah. Let's go ahead. They also provide a short description on SPI BB, which is the bootstrap version, I guess. Let's see. Follows behavioral policy in less explored state action pairs while attempting improvement elsewhere, everywhere else. Okay, assuming they know the behavioral policy, so you should know mu. Okay. However, we find these algorithms have failure modes even in simple MDP shown in figure 1. Okay, let's get back to the figure 1. Yeah, so MDPs are simple chain MDPs, okay, which have less number of states, and the notable point is that these are the few extreme cases, I guess. Like if you see the value of mu here, which is 0.99, so it's really high, and once you start in S0 or S1 states, you would end up in S2 state with 90% probability. So yeah, let's see this combination lock. Let's see. You would start in S0 with 0.5 probability. You would go to S1. Okay, you would go 50% chances to the left, and every time in every state you would end up in S10 state with 50% probability. But what about the reward? Yeah, the reward is the highest at S10 state, although reward it is minus 0.5. So yeah, you would need to explore like 10 states before knowing which state is. Yeah, so exploration is heavily required here. So yeah, let's see. Yeah, if you see in this figure 2, the first figure, the MDP with rare transition, the first figure, yeah, these two are linked. So if you see the green curves, these are the algorithms in the current paper, MBS QI, which we'll look at details in this video later. So let's see what they're saying here. So it starts to C, unsafe states, yet followed by B. Yeah. So let's see. You see unsafe states and the algorithms like SPIP quickly fall the success rate because they are just following the dataset policy in the unseen states. But even the behavioral policy won't be an optimal one in these unsafe states. So yeah, but they say that although the when data set increases, the performance of SPI BB also increases. So yeah. The next figure is for the combination lock MDP. So here, as you can see, the MBS QI and PI are performing really good. So the other algorithms are BCQ and Bear. Yeah, they're really overestimating the states here. So it's like they might have been overestimating the reward which you would achieve at the 10th state coming from here. So yeah, let's go ahead. Yeah, just to add a point here that Bear is the same as BCQL with non-zero threshold. So this one is Bear. So yeah, going ahead. Yeah, I talked about this in the above figure. So let's go ahead in the most important section where on the algorithms of the current paper. So yeah, marginalized behavior supported algorithms. Let's try to decode these keywords later. Let's see. Our aim is to create algorithms. Okay, API versions. So since they're using functional approximation, if FQI and FPI are the counterparts of ABI and API. So for FPI you would need a richer policy class like this. Yeah, and FQI you would need the Q function class like this. Yeah, you would need the usual assumptions on these things, like you would need to have compactness assumptions like y and f are both finite with error bounds depending on log f, cardinality of f and cardinality of pi. Yeah, let's go ahead. They define the weighted norm here, the p mu norm. Okay, now this is where you would find the least squares version of the ABI or API updates. So FQI update is this way. So you would use the previous samples using the Bellman update as the target and try to fit to the function using the L2 square norm or the weighted L2 norm and minimize over that. Yeah, this is the fitting problem. So yeah, this is how you would decode this function, this optimization. So yeah, similarly FPI also has similar structure where you iteratively do this step. Yeah, where you don't have where you directly get the policy by using the greedy approach instead of going through policy evaluation and the improvement step separately. So yeah, now I think there is a note here which says both AVI and API suffer from bootstrapping errors in less visited regions of MDP even in the tabular setting. Okay, FPI and FQI will also have the same drawback. So yeah, even this suffers with quite a bit of overestimation. So that is what being said here. So let's go ahead. Okay, now show how to design more robust algorithms by constraining the Bellman update to be only over state and action pairs that is sufficiently covered by mu. Okay, so the usual thing. Okay, given we have samples of this distribution from the mu, several density estimation techniques can be used to approximate mu. Okay, so yeah, you would can find estimator mu hat for mu, which gives you the law of mu hat is really close to the law of mu, and the estimator uses the data set. So yeah, here they define a filter function called xi of SA, which you drop mu hat and b. It's an indicator function. You can say that you are only looking at the densities with good densities. The goodness is characterized by this hyperparameter b. So yeah, they further say that since this is an hyperparameter, you have more flexibility on the concentrability coefficient kind of a thing, where you don't have this explicit behavior. So yeah, let's go ahead. They define a composite function. Yeah, now they introduce MBS PI, so which is to algorithm 1. Yeah, let's go ahead with reading this text. Yeah, the algorithm 1 just says that you would first fit the function to the least squares and do the policy update using a policy improvement step, and here you would directly iterate over the function space and use a greedy policy. So yeah, Let's go ahead with the text rather than this pseudocode. So now getting back here. So yeah, manual modification of vanilla API is made. So which is this part where they add the filter function, which encapsulates the constraint of the dataset policy. So if you see BCQ or pair, even they are using similar constraints on their update steps in the Bellman operators, but they typically tend to assume that they know the dataset policy mu. Here, the filter function is dependent on mu hat, which is an estimated version of mu. So which can be made close, and you can use the state-of-the-art results from information theory for such estimators. That is not a bottleneck as for this paper. I mean, I should not say bottleneck, but yeah, it's not the concern of this paper to to develop a good estimate of mu hat for mu. Instead, they can just use the SOTA results from information theory is what I meant. So okay, yeah, let's go ahead with the algorithm description here. So yeah, Bellman evaluation is defined this way. This is just an from the previous Bellman operator, but here you would add this filter function. So yeah, so you would use the least square function, but it's the usual least squares. Just the filter function is being added here in the step. And again, for the MBS BI version, it's just these additions here to the previously presented Bellman operators. Yeah. Let's go ahead with some of the text provided here. Like the threshold B is the only hyperparameter needed for our algorithms. Individually B traits of the risk of extrapolation. Yeah. So yeah. Let's go ahead with the analysis section. Policy, okay. Output by the MBS PI and MBS QI result is similar, okay. Complete proofs are provided in the appendix, okay. So I'm just putting this out here that interested readers can go through the appendix, because the appendix is really long. I mean, it is having, the number of pages is at least 20, so yeah, I would not be able to go through in the video, so, and I would just bore you. So yeah, it's on the personal researchers who are currently using these results in their research. So yeah. So here they define few terms. Eta parameter, it's the usual okay, it's the marginal distribution of SH, okay. So yeah, probability space with the support of states given the policy pi, okay. So they also have for each time step, okay, and they also have for the pair SA, which is just the product space of product of these two product probability distributions, eta h pi of s and the pi policy itself, and they remove h by the usual discounting sum. Okay, so yeah, a few assumptions which are made here. Yeah, let's go through these. Bounded densities. So first, non-stationary policy pi and h, they have this boundedness assumption. As you can note from the above definition of eta of s and a, this implies this is true. Yeah, so yeah, this is just one of the observations. Yeah, you would say that since this is a probability distribution, you can trivially bound it by 1, but note it might not be the finite states and action space which you are considering here. It is the infinite state and action space. Continuous state space and action space considered here. So yeah, for continuous random variables, this might not be true. So I mean, these are the densities, right? So yeah. Let's go ahead. I just wanted to bring this point because this gives some impression that you are considering PMFs rather than PDFs. So yeah, I just wanted to. In general, PDF can be defined. Okay. Probability density function. So yeah, just keep that in mind. So as you can see, the assumption is also named after densities. So yeah. Now the second assumption, yeah, it's just the estimator assumption that your mu hat and mu are close enough. You can look at info theory results for getting a better estimator, but here they use the usual MLE estimator, which gives 1 over root n error, where n is the number of samples from the data set. So assumption 3 and yeah, I think assumption 3 and assumption 4 are follows from the usual FPI and FQI analysis. So but you have to just include the filtration functions. So yeah, here and here. Yeah. Yeah, so let's go ahead. The data set may not have sufficient samples of state and action pair under optimal policy in order to reliably and confidently return the optimal policy. Yes. So in fact, your dataset policy need not be optimal itself. So yeah, that is one of the challenges in this offline setting. And they promise that will return a policy which is close to the best policy, which has sufficient support in the provided dataset. Yes, pi star over the support, which spans over the dataset policy. Yeah, so let's go ahead with the definition here. Xi constraint policy set pi all c. I think they are missing for all state and action pair condition here. So this filter function for a pair SA is 0 given pi is bounded. So yeah, I just wanted to add a point here. The second thing here can be expanded in this way by the definition of eta pi density. And then just wanted to mention that you could just bound this by 1 and you would just get the eta pi of SA, and which is bounded by capital U by assumption 1. I don't know how the epsilon xi depends on U and B supposedly. I don't know. That is an interesting observation, which I think. So yeah, if you have some pointers towards this, please let me know in the comments. Here, I think the C, they mention it here, like C is equal to U or B, which is like the concentrability assumption, but it's like you have a choice of choosing B. So yeah, it's in your hands. Yeah, now they provide a result lower bound for the value of policy returned by their algorithm by any value pi tilde up to the small error. So yeah, this is the important theorem. So let's go ahead with the corollary one, which is the more practical result. In the sense, you are just choosing your pi tilde to be pi star, then you would get the corollary one statement, which is here. So yeah, there is a type of missing a full stop or a period here. So yeah, if the authors happen to see this video, they can correct these typos. There are very less typos in the first place. So now let's go ahead with the yeah, I can quickly talk about the proof sketch here. Yeah, it's really minimal, so just bear with me a few minutes here. So they construct a temporary MDP M prime, which is like you are adding a man-made action for each state space, so that you would end up with at the absorption state ABS. So yeah, it's like well, if you want to bound this parameter VMIT, you would first bound with something like this, which depends on M prime rather than M, and then these parameters might have really simple characterizations. So that is one of the reasons which people do construct these auxiliary MDPs. You could see similar ideas used in model as well. So yeah, yeah, I mean, just putting out one of the quick ideas here, like since this is a very similar to model, you could as well use M prime as your model and do the model based RL approach, algorithm. So yeah, so I think the current paper implicitly solved model-based algorithm. I mean, implicitly came up with a model-based algorithm rather than model-free. Yeah, it's like they have done both. So I think they can comment on this point. If any of you are interested, you can just write another paper using these results as a model-based paper. So yeah, let's go ahead with the text here rather than my own points here. So let's go ahead. Our results match in N, the first rate of ABI and ABI, and the bound is having the cubed root of 1 over 1 n as gamma, which is the usual bound which you would get in the using the monosis type of argument. So yeah, let's go ahead. Yeah, just to quickly show you the assumption in the corollary one is that your optimal policy pi star should be one of your pi tilde, which is in this policy space. So thus you have to make this assumption, so that this would imply your pi star belongs to pi. So yeah, this is one of the reasons, one of the assumptions which you should make. Let's go ahead. So using the completeness assumption which I just mentioned above, and this part, the error bound from theorem 1 is simplified to this factor. So yeah, so what this is saying is whatever your algorithm gives out the policy as, the value of it is at least close to your optimal value, but like far away in this order. So let's go ahead with the text here. When comparing to the on policy optimization, the constancy is akin to the density ratio, okay, which we repeatedly looked at. Completeness can be avoided by Monte Carlo estimation in policy. Okay, there is no need for density estimation to regularize value. Okay, this is regarding the on policy versions. So yeah, let's go ahead with the results provided in this paper. If we can find behind this thing, okay, given sufficient data, then theorem 1 immediately yields a policy improvement guarantee 2. Yes, I mean up to this constant. So now they also provide a safe policy improvement guarantees, which is to say that this parameter will be replaced by the value from the dataset policy. So you would assume your dataset policy is good enough in some sense, so you would not want to deviate from it in terms of the return. So this characterizes some kind of safety, but yeah, I don't know, I can make a comment that what if your dataset policy is a suboptimal one and not quite safe, and it is quite aggressive in nature, Does this kind of bound imply that you are safe? Yeah, I mean, that is one of the alternative questions, I guess. So, yeah, the corollary 2 follows from the theorem 1 again. But yeah, they provide two corollaries, one for the discrete action space and one for the continuous space, I guess. Yeah, as you can see here. Yeah, I won't be going through the details of the constants provided here. So yeah, to just to summarize, first, compared to prior work, which provides guarantees of the performance relative to optimal policy under consentability, we provide similar bounds, okay, with respect to optimal policy and as well as the dataset policy. And with respect to dataset policy is said to be safe. Okay, sure. Moving on to the experimental results. Yeah, I'll be really quick at presenting this sections. Okay, so let's see. This I is the filter backer from unsound state and action pairs. Yeah, that is because you have an indicator function says that is greater than b. So all the unsound actions which is parameterized with this hyperparameter b is discarded. So yeah, that is the point here. So they have experimented on the cardboard and Mujoko tasks. So yeah, and utilize a different Xi estimation procedures. So from being inadequate, okay, complete got it. So basically, different kind of data sets are being generated. Our algorithms return policies better than any baseline patch error across entire spectrum of dataset. Okay, compared to BCQ Bear and SPI BB, I guess. And then the algorithms presented here, the hyperparameter B to trade off the conservatism of the large B. Okay, that is the advantage over the concentrability condition which the previous works had. So yeah. Yeah, they just set in the discrete spaces, they set b to be this parameter where n0 is the number of samples prior. N0 is our prior for the number of samples we need for reliable distribution estimate mu hat, and n is the total samples. Okay, so yeah, is this close to 1? No, it shouldn't be. Yeah, you will need to look at the code to decode this. Let's go ahead. We can set the threshold percentile, okay, mu hat for the Xi function. You can also run post hoc diagnostics on the choice of b. Okay, the like a line search sweep, like evaluate for different values of b and then pick the best b by using some kind of validation analysis. So let's go ahead into the discrete experiments where MBS QI is used. Yeah, this is appropriate for the discrete spaces because you have the direct policy update instead of going through the policy evaluation and policy update steps like in the MBS PI. So yeah, card pool v0 is being used. There is only two actions in card pool v0. Yeah, binning of each state dimension, resulting in 10,000 states. Okay, the continuous state space is being reduced, is discretized here. So FQI and FQI is being ran, BCL is ran, and then SPIB. Okay, then let's get into the figures here. So they collect 10 power 4 transitions from epsilon greedy policies for as the data set policy, and then they also report final policy value from different algorithms for epsilon 0.0 to 0.1, which is in this left figure here. So this is just the dataset policy, and for epsilon 0.3 this is the thing, for epsilon 0.6 this is the policy. So corresponding to these, this is a figure, corresponding to this is a figure. So in both of these settings, as you can see, MBS QI is performing better than outperforming the other things. Yes, and the behavioral cloning version as well. Surprisingly, as you can see, the second, when epsilon is 0.6, SPI BB is like performing very close to MBS QI. Maybe the since both are constrained or the Bellman operators, and both are having some kind of policy improvement steps, yeah, that might be the reason for having this kind of behavior. Yeah, this is just pure speculation. I don't have any clear-cut answer for that. Let's go ahead with the next section where they provide the experiments for continuous spaces. So here, yeah, let's see, MBSQL. Okay, it's a extension of the normal MBS, which incorporates on top of BCQ. Okay, so, and a variation to a VA autoencoder to approximate the policy space. The filter function is the evidence lower bound by the VAE autoencoder. Okay, P2 is the second percentile of elbow. Yeah. I won't go into the details. So here, the data set is collected by imperfect batch from some kind of greedy policies, epsilon greedy policies on top of the continuous spaces, as you can see here. And then this is the figure where MBSQL is outperforming every other SOTA results. Let's go ahead. Okay, let's talk about the related work. I think I just added more related because they have already talked about BCQ, Bear, SPI, BB in the earlier sections. Let's see what more does this section have. So Yeah, for practical settings, functional approximators, fitted values to many prior works provide error bounds, evaluation on the concentrability coefficient. Okay, our goal is to relax the assumption, okay, which is why they come up with the hyperparameter B. Yeah, this is equivalent to the concentrability coefficient C. Now this paper provides simple modifications and strong theoretical guarantees, even with functional approximation. Theoretical results of Bayer rely on the finite state space, while the algorithm analyzed in the proof is actually the same as BCQL with non-zero. Okay, I don't want to say anything regarding that. Let's see. Also, recent work highlights sufficiently large diverse dataset can lead to good. Okay, yeah. Let me just see what this. Okay, this is the Rishabh Agarwal's ICML work. Yeah. Let's end this video by discussing the last few sections here, which are the conclusion section. Yeah, I think I have repeatedly talked about these things in the earlier sections. I'll just skip this. Maybe the broader section will have broader impact. I'll have something. Let's see. Sample efficiency of online RL and safety of policy can be improved. Yes, due to the work in offline RL. Yeah, we caution that more work is needed. Yes, this is the usual terminology used for the impactness property. So, just to make sure that they acknowledge that the current result is not exactly the practically implementable SOTA, but yeah, it has some disadvantages like any other algorithm out there. So yeah, let's see about the some positive statement here, like no batch algorithm has low variability across runs, very reliable terminates when discovering good policies, give sharp confidence interval of expected performance. So these are 3 points in which is addressed in batch RL can be helpful in off policy evaluation method. So yeah, let's see. Yeah, thank you for listening this video. Hope you enjoyed the video. I'll be posting a few more on offline RL. Keep a lookout at this playlist. If you have any comments, if you have any suggestions, please comment. Use the comment section, and as usual, I'll be adding a detailed description in the description box of the YouTube. So yeah, thank you.